Welcome to the Introduction to Intention Space series from IntentixLab in Melbourne. In this series, we will explore a simple but powerful question. How can we bring AI into deterministic enterprise systems without losing human understanding? Today, most AI interaction happens through natural language, while most enterprise execution depends on deterministic software. Intention space begins from the idea that we need a common interface between the two, a natural language structure that AI can work within, humans can understand, and machines can execute deterministically. The open secret is that this interface already exists in communication itself. Intention space shows how to make that interface explicit, bounded, and usable at scale. Welcome to the episode 1 of Introduction of Intention Space series. Every software system performs computation. As software engineers, we spend our lives designing computations, optimizing computations, and more recently, asking artificial intelligence to generate computations. But today, I would like to begin with a different question. What exists before computation begins? The communication force within language. Language is one of humanity's greatest inventions. Through language, we do not merely describe the world. We ask, we promise, we warn, we invite, we teach, we coordinate our actions with other people. Living together in society has allowed us to use language as a means of shaping our shared reality. Every culture develops and protects its own language because language carries something far more valuable than words alone. Today, large language models have become remarkably capable of generating language. This naturally leads to a deeper question. What is it that language actually carries as it communicates? Programming is still communication. When we program a computer, we use a programming language. Although its syntax is different from everyday language, it is still an act of communication. Think about ordering a coffee. I simply say, 1 flat white. Perhaps I make a payment. That short interaction carries everything needed for the coffee shop to understand my intention and respond appropriately. The distinct words, the context, and the expected outcome all belong together. Traditional programming took a different path. We separated communication into two distinct parts, instructions and data. That abstraction made software engineering possible. But in doing so, we also separated things that language naturally keeps together: the intention, the information that supports it, and the distinctions that tell us what this communication is about. When I say 1 flat white, the number 1 is not the same kind of meaning as flat white. 1 gives a quantity. Flat white distinguishes the thing being asked for. Traditional software often flattens both into data. Today, I would like to show you that we no longer have to rely on that flattening. By making intention explicit, we can allow computation itself to remain bounded by the same communication that gave rise to it. And later, through pulses, we will see how the distinctions carried by language can also become part of the fabric of computation. Intention, the missing ingredient of communication. Throughout our lives, we communicate with other people almost effortlessly. We rarely stop to explain our intention in detail. Our families, our workplaces, and our societies already provide a shared context that helps others understand what we mean. When I walk into my favorite coffee shop and say, 1 flat white, please, I do not explain what coffee is. I do not explain how it should be made. I do not describe the sequence of actions that the barista should perform. The intention is already understood. Human society, its norm and structures, have evolved to carry intention implicitly through communication. Computers do not possess that shared social understanding. Yet, when we build software, we often assume that intention can remain implicit there as well. As a result, software communicates instructions and data, but not the purpose that naturally binds them together. Intention space begins with a different proposition. Instead of leaving intention outside computation, we make it explicit. Once intention becomes explicit, it can provide the boundary within which data has meaning and computation takes place. That simple change opens the possibility of a different model of computing. Design node, the agency of intention. If communication carries intention, then there must also be something capable of responding to that intention. When I ask for a coffee, the barista responds. When I ask a colleague for help, my colleague responds. Communication is always completed by some form of agency. Computation is no different. Every computation begins when some computational agency receives an intention and decides how to realize it. In intention space, we call this agency a design node. A design node is not defined by the algorithm it executes. It is defined by the intention it is capable of realizing. Once an intention reaches a design node, the internal algorithm is free to choose the most appropriate way to fulfill that intention. The outside world does not need to know how the design node works internally. It only needs to know what intention the design node is responsible for realizing. This simple viewpoint allows us to treat software components, AI models, services, hardware devices, and even human participants in a remarkably uniform way. Each can be viewed as a design node, a bounded agency whose purpose is to realize an explicit intention communicated through a canonical structure called a signal. Signals, carrying explicit intention. If intention is made explicit and design nodes are the agencies that realize intention, then we need a way to communicate that intention. In intention space, that communication is carried by a signal. A signal is more than data. It carries an explicit intention, together with the contextual information needed to realize that intention. We call these contextual elements pulses. Consider ordering a coffee once again. The intention may simply be, prepare a flat white. The pulses provide the surrounding context. 1 sugar, almond milk, extra hot. If almond milk is unavailable, use oat milk. The intention defines the boundary of the communication. The pulses describe the current situation within that boundary. Together they form a signal. A design node therefore performs a remarkably simple task. It receives one signal. It realizes the intention carried by that signal. It emits another signal. From this point onwards, computation can be viewed simply as a progression of explicit intentions flowing between design nodes. Signal, design node, signal. Signals in and signals out create the boundary in which a DN operates to realize one intention. The bounded corridor for the intention processor, with the design time specification of a design node as signal in and signal out. We can see the general intention processor as a human, an AI, or an automated code generator. The point is that the intention processor works inside the narrow corridor of two defined signals. Confined within the specified intentions, that role can be fulfilled by combining a general specification with the input-output signal pair to produce testable code. First intention processor, user login. Up to this point, we have been building a model. Now, let us see the model in action. User authentication is one of the most familiar computations in software engineering. Traditionally, we begin by thinking about APIs, databases, sessions, and authentication frameworks. In intention space, we begin somewhere else. We begin with the intention. The design node does not initially need to know how authentication will be implemented. It only needs to know the intention it is expected to realize. The incoming signal expresses that intention. Its pulses carry the contextual information, such as the username and password, that the design node can host as an intention processor that receives this bounded specification. Within those explicit boundaries, an LLM is able to generate the design node. Notice what is happening. The LLM is not being asked to invent a complete application. It is being asked to realize one explicit intention. The generated design node is then registered in the design node registry, ready to participate in larger computations. What has been generated is not merely code. It is a computational agency capable of realizing one explicit intention. Second intention, processor histogram generation. Was the previous example special because it dealt with user authentication? Let us try something completely different. Suppose our intention is to create a histogram from a supplied data set. Once again, we do not begin with an algorithm. We begin with the intention. The incoming signal states that a histogram is required. Its pulses carry the data together with any contextual requirements, such as titles, colors, or bucket sizes. The intention processor receives exactly the same kind of bounded specification as before. The only thing that has changed is the intention. A different design node is generated. The new design node is executed within its signal context. Computation remains a uniform flow: signal, design node, signal. This demonstrates an important property of intention space. The computational model does not depend upon the application domain. Only the intention changes. Everything else remains remarkably uniform. As more design nodes are generated and registered, increasingly sophisticated systems can be assembled simply by composing explicit intentions. Composition: login plus histogram. We have now generated two different design nodes. One design node realizes the intention of user authentication. Another design node realizes the intention of histogram generation. Each was generated from its own bounded inference specification. Each has its own incoming signal. Each has its own outgoing signal. Now we can ask a more interesting question. Can these independently generated design nodes participate in a larger computation? Let us compose them. The login design node receives a login attempt. It emits an authenticated signal. That authenticated signal now becomes part of the context in which another intention can be realized. The histogram design node receives the histogram request, together with the authenticated context. Now the histogram is not generated in isolation. It is generated inside a richer intentional situation. This is the deeper point. Design nodes do not need to call one another directly. They compose through signals. The output of one realized intention can become part of the context for another. The important result is not simply that login and histogram work together. The important result is that two separately generated computational agencies can be composed because their boundaries are explicit. That is the beginning of intention space as a software architecture. So, what has changed? Let us step back. We began with a question: what exists before computation? We saw that language carries more than words. It carries intention. We saw that programming is also communication. But traditional software separates instruction and data, while leaving intention mostly implicit. Intention space proposes a different starting point. Make intention explicit before computation begins. Once intention is explicit, it can define the boundary within which data has meaning. That boundary is carried by a signal. A design node receives that signal, realizes the intention, and emits another signal. The intention processor uses this structure to generate executable design nodes through bounded inference. The generated code may be JavaScript today. It may be Go, Rust, Python, WebAssembly, or another language tomorrow. That is not the essential point. The essential point is that the design node is defined by its signal boundary, not by the programming language used to implement it. This makes the generated computation replaceable, testable, and composable. As AI models become more powerful, the question is not only what they can generate, the question is how we choose to bound their inference so that they realize explicit human intentions. That is the purpose of the intention processor, and it is the first practical step into the wider journey of intention space. In future episodes, we will explore how design nodes, signals, and bounded intentions compose into larger structures for software development, AI usage, and eventually richer forms of human-machine collaboration. For now, the central idea is enough. Intention exists before computation. By making intention explicit, inference itself can be bounded before code is generated. As AI models become increasingly powerful, the question is no longer how much intelligence they possess. The question is how we choose to bound that intelligence so that it reliably realizes explicit human intentions.